All right, continuing with chapter 9, which is about mathematical modeling. We are in 9b. So we have two sections left to cover. 9b, which is on modeling with linear functions, okay, so lines basically. And then 9c, which is also going to go up at the same time as this one, is on modeling with exponential functions. So a lot of this section is going to be familiar to you from high school or other math classes you may have had, in that we're just looking at lines. So we'll look at some of the familiar concepts like slope and y-intercept and slope-intercept form, and then see how we can apply that to solving problems. So a linear function has a constant rate of change and a straight line graph. Now recall from 8a, section 8a, that we said linear growth is growth that occurs by adding a constant amount per unit of time. That's where that constant rate of change comes from. And that constant amount that we add to get linear growth, that is the slope. The slope tells you how much you add per unit of time. The rate of change is equal to the slope of the graph. The greater the rate of change, the steeper the slope. And you calculate the rate of change by finding the slope between any 2 points on a graph. So the rate of change is the slope, which is the change in the dependent variable over the change in the independent variable. So here's an example with a line of what that previous thing was saying. To find the slope of a straight line, look at any 2 points and divide the change in the dependent variable by the change in the independent variable. So here's a straight line. Pick 2 points on it, point 1 and point 2. This is the change in the independent variable, the distance from along the x-axis, the distance on the x-axis from point 1 to point 2. And here's the change in the dependent variable, the distance along the y-axis from point 1 to point 2. So let's look at that in a little bit more detail and use a little bit more familiar notation. Now the slope, which we're usually just going to write that as m. I'll go ahead and put that now, even though we'll introduce it formally later. This is the change in the dependent variable divided by the change in the independent variable. Okay, so let's suppose that point 1 has coordinates x1 comma y1. That is, down here on the x-axis, this would be x1. Over here on the y-axis, this would be y1. And just notice how messy that looks. Let me see if I can clean that up a little bit. This should be x1 comma y1. And then point 2, suppose point 2 has coordinates x2 comma y2. So down here on the x-axis, this would be x2. And over on the y-axis, this would be y2. So the change in the dependent variable, that is from y1 to y2, that's just going to be y2 minus y1. So this numerator up here is y2 minus y1. And the change in the independent variable, going from point 1 to point 2, that's just going to be going from here to here. Well, that's just x2 minus x1. So this is x2 minus x1 here in the denominator of the formula for slope. And so we get the familiar formula for slope, where m is equal to y2 minus y1 over x2 minus x1. And so here we have an example. This is an example of a price demand function. So a small store sells fresh pineapples based on data for pineapple prices between $2 and $5. The owner created a model in which a linear function is used to describe how the demand, which is the number of pineapples sold per day, varies with the price. So one thing that the owner of the store found was they found this point on their linear model. That is $2 for the independent variable, 80 pineapples for the dependent variable. What that means is when they price them at $2, they sell 80 pineapples on average. Okay, and we want to figure out what is the rate of change for this function, and we'll talk about the validity. So on the next slide, we're going to get another point because remember, you always need 2 points to calculate slope. So the other point that they have on their model is this one. So when they sell for $2, they sell 80 pineapples a day. When they sell them for $5, they sell 50 pineapples a day. And that makes sense. When pineapples are more expensive, they're going to sell fewer of them. So if we put this if we graph this, that is, if we put the point 280, $2.80 pineapples, and the point 560, I'm sorry, 550, that is $5.50 pineapples, and then draw the line between them. This is what it looks like. Okay, and so remember, the rate of change of a function is just the slope. So all we're calculating here is the slope. Okay, so we can think of it like this: the rate of change which is the slope, is the change in the independent variable along the y-axis. The change in the independent variable is going from the first point to the second point is 50 minus 80, and the change in the dependent variable along the x-axis going from the first point to the second point is $2 minus $5. So that's going to be sorry for that pause. I just realized that I had that backwards. And that's actually good because this matters a lot when you're calculating slope. Since I started with 50 in the numerator, I need to start with $5 in the denominator. And then I ended with 80 in the numerator, so I need to end with $2 in the denominator. So what I'm saying is 50 minus 80 divided by 5 minus 2. Because you see how the $5 and the 50 goes together? They go together here. The 2 and the 80 go together. They go together right here. So if you do the arithmetic, this is going to work out to be negative 30 divided by $3, which works out to be negative 10 over $1. Now, let's think about what this means. Negative 10 means they sell fewer pineapples. The number of pineapples they sell go down. And how does it go down? By every time the price goes up by $1, the number of pineapples they sell goes down by 10. So for every dollar increase, they sell 10 fewer pineapples. Again, for every dollar that the price increases, the number of pineapples sold decreases by 10. So as the cost goes up by $1, the number sold goes down by 10. As far as validity goes, this seems like a pretty valid model. It's a simple, all it involves is just the cost. And as long as they don't start selling like, huge numbers of pineapples wholesale or something, if they're selling to the public, this seems like a pretty good model. It makes sense that as the price goes up, they're going to sell fewer pineapples. And here we have something called the rate of change rule, which in a minute I'm going to write this in terms of x's and y's, and this will be something a little bit more familiar with. The rate of change rule, what it does is it lets us calculate the change in the dependent variable from the change in the independent variable. So if I want to know how does the dependent variable change, well, it's just the rate of change multiplied by the change in the independent variable. So remember, we usually use x's and y's, that we usually use y's for dependent variable. So this is the change in y is equal to rate of change is the slope multiplied by the change in x. Now, change in y is just y2 minus y1, Slope is written as m, and change in x is x2 minus x1. So this is what's known as the point slope equation for a line. It's the point slope equation for a line. But we can actually figure some things out from problems just by regarding it in these words, where the change in the dependent variable is the rate of change times the change in the independent variable. And here's an example how we can do that. So we want to use the linear demand function in this picture right here, which is probably too small to see, but it's just the same one we had before, and predict the change in demand for pineapples if the price increases by $3. Okay, well, what's the independent variable? The independent variable was the price of pineapples. That's the one that the store owners can control. And the dependent variable is the demand for pineapples. It's how many they sell. So the rate of change rule in this case would be change in demand is equal to rate of change times the change in price. Well, the change in demand is what we're trying to figure out. That's what the example asks us to figure out. And we know what the rate of change is. We calculated that. The rate of change is -10 for every $1. And the change in price is given to us. The change in price is it goes up by $3. So that's $3. So dollars cancels with dollars, and we're left with -10 times 3, which is -30 pineapples. In other words, if they raise their price by $3, they're going to sell 30 fewer pineapples. That's what the negative sign tells us. They're going to sell -30 pineapples, or 30 fewer pineapples than they would if they didn't raise their price by $3. Now, here's something that you've seen before, but not described like this. This is what I'm going to call the general equation for a linear function. The dependent variable is equal to the initial value plus the rate of change multiplied by the independent variable. All right? So think about if you have the graph of a line, okay? There's my x-axis, and there's my y-axis. So I'm just going to draw a line on this graph. And suppose this line has slope m. So the dependent variable is what we usually call y. I'll come back to initial value. The rate of change is slope, which is m, and the independent variable is x. Now, it's probably already occurred to you that the letter that's left out of this is b. All right, this is the wrong order, but you should have this drilled into your head, y equals mx plus b. Well, this is what that means, okay? This initial value is right here. That's b. That is when x is 0, when x along the x-axis, when we're at 0, that's going to be the y value. That's what's called the initial value, b. So the general equation for a line is the dependent variable equals the initial value times the rate of change, plus the rate of change times the independent variable, or y equals b plus mx. Or the way we usually think of it is y equals mx plus b. So let's talk about how we can graph an equation if it is given to us in this general form. Okay, so the equation y equals 4x minus 4 is a straight line with a slope of 4 and a y-intercept of -4. And here in the right, I'm going to graph it. Now, the only thing you need to graph a line is 2 points that are on that line. So we know that, remember, y equals mx plus b is that general form, where b is my y-intercept, the initial value. Well, this is a -4, so that means that -4 is a point that is on my line. So how do I get another point on my line? Well, I know that the slope is equal to 4. That's given here. And something I didn't talk about before, but remember, slope is rise over run. Okay? So 4 is the same thing as 4 over 1. So we rise 4 and run 1. So rise, from the point you have, rise 1, 2, 3, 4, and then run 1 to here. And so the line that we want is going to pass through those 2 points. So let's see if I can draw a line that passes through those 2 points. No, it doesn't work. Let's do this. Oops. So I'm going to start here and draw the line this way. And to extend it, I'm going to just do this. So pretend those match up, okay? But that is the line that passes through those 2 points. So this is my line, y equals 4x minus 4. And if I draw that triangle, let me use a different color. If I draw the triangle that I get from here, the change in my independent variable is 4 because I rose 4, and the change in my dependent variable is 1 because I ran 1. So my slope is 4 over 1, and here my y-intercept is -4. So remember, to draw the graph of a line that's in this form, you plot the y-intercept and then you do rise over run from your slope. So this is just some information to remind you of. When you change the slope of a line, when you change the slope, it changes how steep the line is. So for example, this red line has a positive slope, so it goes up to the left. The blue line has a 0 slope. That's a horizontal line. Remember, slope means rise over run. This one isn't rising at all. And if I have a negative slope, the black line, then it's rising in a negative direction. In other words, it's falling as you go to the right. So this is what happens when you change the slope. It changes how steep the line is, and it can even be flat, and it can even go down. And this graph shows what happens if you change the y-intercept, right? If you change the y-intercept, you get a bunch of parallel lines. So here's an example of what happens if you have a y-intercept greater than 0. The line is going to cross the y-axis above the x-axis. Here's what happens if you have a y-intercept equal to 0. The line is going to pass through the origin right here. And here's if you have a line with a negative y-intercept. It's going to cross the y-axis under the x-axis. So changing the slope changes the steepness of the line, and changing the y-intercept gives you a bunch of parallel lines. It changes where the line crosses the y-axis. So in this example, we want to use this function shown over here to the right to write the equation. Okay, so we're given the function, the graph, we want to write the equation that describes the rain depth at any time after some storm begins. This is an equation that tells us how deep the rain is a certain number of hours after a storm starts. And we're going to use the equation to find the rain depth 4 hours after the storm began. All right, so to write, so the equation we're going to be using is this one, y equals mx plus b. So remember, y is your dependent variable, x is your independent variable. So they stay what they are. They are y and x. Those variables are y and x when we write the equation. So what we have to figure out is what's m and what's b. Those are the two things we have to figure out. Well, b is where it crosses the y-axis. This line crosses the y-axis at 0. So that tells us that b is equal to 0. Okay? Now, how do we find the slope? We pick any 2 points we want on the line and do rise over run. So let's just pick this point, and let's just go to this point and see what we get. Do rise over run. Well, this is the point, this first one, this is the point 3 comma 1.5, and this one, that's the point 4 comma 2. So if we calculate the slope, m, that's going to be 2 minus 1.5 divided by 4 minus 3, which is just going to give us 0.5 over 1, or 0.5. So that's my slope. My slope is 0.5. So that tells us that the equation we're looking for is y equals m, which is 0.5x, plus b, but b is 0. So this is the equation of the line. So this line right here, this is the line y equals 0.5x. Now, to answer the second part of the question, find the rain depth 4 hours after the rain began. So 4 hours means that x is equal to 4, because that's what this is measured in. So we'll just plug that in. Y equals 0.5 times 4, which is 2. So 2 inches. So 4 hours after the rain began, there will be 2 inches of rain according to this linear model that we have for rain depth. And now we come to the last thing to cover out of this section, and that is creating a linear function from 2 data points. All this is really saying, okay, all this is asking you to do, I'm going to write this parenthetically, this is write the equation of a line if you're given 2 points. That's all this is talking about. How do you write the equation of a line if you're given 2 points that are on the line? Step 1, let x be the independent variable, y the dependent variable, and then find the slope. All right, you have 2 points. You can find the change in y, you can find the change in x. That is, find your slope, which is y2 minus y1 over x2 minus x1. Step 2, substitute the slope and numerical values of x and y from either point. That is, you pick one of your points. It doesn't matter which one. And you sub in m, you sub in x, and you sub in y into this equation, and that will tell you what b is. Then you use the slope and the y-intercept to write the equation in this form. Let's do an example. So until about 1850, humans didn't use hardly any crude oil at all. We used almost none, all right? But then by 1960, humans had used a total of 600 billion cubic kilometers of oil. Use a linear model to describe the world oil use since 1850. Discuss the validity of the model. All right, so what this is saying is write an equation that, that describes how much oil is used. So we're going to let x, the variable x, this is going to be the year. And we're going to let y be oil used in billions of cubic meters. So then our 2 points are going to be point 1 in the year 1850, we basically used no oil, so 0 oil. And then point 2 by the year 1960, only 90 years later, we had used 600 billion cubic meters of oil. So using those 2 points, we're going to make a linear model. So again, our 2 points are 1850 and 0, and our other point is 1960 and 600. So the slope of our line is going to be change in the dependent variable, so 600 minus 0 divided by 1960 minus 1850. So 600 minus 0 is just 600. 1960 minus 1850, that's 90. So this is 60 over 9 by just canceling out these zeros. Let's see how far we can go in our head. Cancel out a 3 everywhere, and we'll have 20 over 3. And I just realized I messed up. Hopefully you all caught it, but let me just go back. That's all a mess up. And I'm going to leave it up as a mess up because I think, like I said once before, it's good for you all to see when your teachers make mistakes, because these mistakes are easy to make, and it illustrates why you need to be careful. The numerator difference was fine. That is 600. But 1960 minus 1850 is not 90. It's actually 110. Okay. And if you plug that into a calculator, you'll get that that's 5.45. Our units were billion of cubic meters of oil, and this is how much is used per year, because that denominator is year. The top is billion. This numerator is billions of cubic meters of oil. The bottom is year. So this is how many billions of cubic meters of oil are used per year. So then finding the equation, we take y equals mx plus b, and I'm just going to use this one. Remember I said you could use either equation you wanted. I'm going to use that one because there's a 0 right there. And I'm going to plug in some numbers, okay? So if I plug in for y, then I would be plugging in a 0 because that's my y. So 0 is equal to my slope, which is 5.45. If I plug in x, that's going to be 1850 because that's my x value. And then it's plus b because b is what I'm looking for. So if you do the multiplication, that's going to be 0 equals 10,083 plus b. And then if you take that 10,083 to the other side, you're going to get that b is equal to negative 10,083 billion cubic meters per year. So putting that all together, our final equation is y equals slope, which is 5.45 x plus my y-intercept. It's a negative, so I have a subtraction, minus 10,083. And this is my linear model. This is my linear model that tells us how much oil is used, cumulatively, how much oil is used every year. Now, we're going to talk about the validity of this model, something you should always think about when you're doing these types of problems in your other classes, okay? So on the next slide, I'm going to have the graph drawn, and we're going to see that this is not a valid model at all, because if we draw the graph of our line and then draw how much oil has actually been used, it's not going to be linear. So let's take a look. So here, this red straight line, this is the graph of the line through those 2 points. It's the graph of the line through those 2 points. But if you actually look at how much oil has been used year by year, it actually looks like this blue graph, which is an exponential model. So think about what we did in section 8A when we had Straight Town and Power Town, how exponentials increase much, much faster. So we're not actually, as a population, we're not using oil at a linear rate. We're using oil at an exponential rate. And the next section, section 8C, is when we talk about how to do exponential fit between 2 points. And that's all for this one.